Okay, can everybody hear me at the back? Good. Welcome to our Guildford Astronomical Society April meeting. Do we have anybody new here this evening? Oh, fantastic. You're very welcome. Can I just ask the committee members to stand up? If you'd like to introduce yourself to them, they'd be very happy to talk to you and explain about the society. Thank you. You can sit down now. Exactly. So yes, this evening we've got a treat. We've got Dr. Paul Daniels talking to us before the break, and then after the break we've got Glenn Bates, who's going to take us on a journey with his T-star. So lots of exciting things to look forward to. Paul Daniels is actually our ex-president, so a friend of the society. He's a fellow of the Royal Astronomical Society, and he's previously been the FAS president, not currently, but previously has been. He's also a member of the Royal Astronomical Society Megaconstellations working group, and has done academic work, and I hope I've got this correct, work on comets, solar system dynamics, and obviously the impact of astronomical megaconstellations on optical astronomy, which is the theme of the talk this evening. So can everybody please give Paul Daniels a very warm welcome. Thank you.
It's great to be back. A lot of new faces that I haven't seen before. Welcome to the new members. I thoroughly recommend Guildford Astronomical Society. As a president for 7 years, they're a great bunch of people and they'll make you feel very welcome. And the money you spend on your membership fee will help you and decide what telescope you want to buy, because there are experts here who are more than willing to help you choose what you buy and get into it. So welcome. So my talk tonight, threats and challenges to astronomy. Occasionally I'm going to say things that perhaps I shouldn't. So I will make the disclaimer that some of my opinions are my own and don't necessarily reflect Guildford Astronomical Society's. Nothing too controversial, nothing to disagree with too much perhaps. So, get this right. Okay, there's a bit of lag. So when I gave this talk previously, I talked about things that threatened astronomy, including terrestrial light pollution. But there are some things that have happened recently in the last 2 or 3 months that really need to be talked about. And I'm already worried that this talk may be too long, as probably are most of you. So the introduction and the history, the way that radio frequencies may interfere with radio astronomy, and then talking about satellites. A lot of stuff here about satellites. And the new stuff here in green is mirrors in space and orbiting data centers, which are the new things that have come up. And then there are elements of the geopolitics. We don't do astronomy in a bubble. We all live normal lives. The world has a life. And as I'm sure you're all more than painfully aware, there are lots of tensions all over the place that may threaten our ability to do astronomy, which may be the least of the worries, but it's important to us as astronomers. So we started out with the visible spectrum. This is the one that our eyes have adapted to over millennia, going from the red through to the violet. And gradually we managed to develop instruments that allowed us to see to the infrared and microwaves and radio waves, things we couldn't see with our eyes, but we had technology to be able to see that. And at the other end of the spectrum, ultraviolet, X-rays and gamma rays. And astronomy, I think, I can't think of another one, but astronomy is probably a science that has the widest range of wavelengths that we observe in, right from the really short wavelength gamma rays and cosmic rays right through to the low frequency radio waves. The part that we can see, the terrestrial light pollution, has grown with the advent of electric lights, street lights, house lights, security lights. And the growth of the urban population, street lights growing not just because we want more of them to light our streets, but because there are more people whose streets need to be lit. And over time, this is obscuring the beauty of the night sky. We're being swamped with radio signals from all sorts of electrically noisy equipment, mobile phones, microwaves, and so on. I've realized that this doesn't work through me. I didn't realize I was so dense. And there's a quote here from Lord Martin Rees. All generations and cultures have looked up and wondered at the stars, but sadly this part of our shared environment has been degraded. Unless they live in a remote rural area, young people may grow up without ever seeing a truly dark, starry sky, and that's a real deprivation. And I absolutely agree. Many of us have perhaps taken children out into a countryside at night and looked up at the sky and they go, wow, what are those? Because they maybe haven't seen stars before. The Royal Astronomical Society has a motto, quicquid nitet notandum, which translates as whatever shines should be observed. But not all of what shines do we actually want to observe. And there is a sort of spectrum of astronomers. We have the prehistoric astronomers who would have looked up at the night sky, looked at the constellations, and will have attached mythical significance to the patterns in the sky and to meteors and to eclipses, and perhaps even have anthropomorphized by treating aurorae as the spirits of ghosts and things like that. And then as time went on, we have the indigenous people, the Inuits and the North American Indians and the Aboriginals. And then we have the modern day equivalent, the family of stargazers who go out and plot around the sky with a pair of binoculars or a small telescope. Then you get the ones who are more serious, the amateurs who meet in a group, and the professional astronomers who put cameras on the back and take time photographs and track the stars with their telescopes. I ought to just interject here because as a sidebar, I generated these cartoons using Gemini AI to generate the cartoons for me. And no matter what I did, I could not get it to generate a reflecting telescope. And some of the things it did with the camera, I don't want to mention. I even told it about reflecting telescopes. It said, oh yes, I know all about those. I said, right, do me a picture with a reflecting telescope. And I got another one with a refractor. So we also have the professional astronomers, the ones that do the research and give the lectures and pass the more detailed aspects of astronomy down to the public. We have those who work, whoops, go back. We have those who work in control rooms, looking at the James Webb Telescope and Hubble Space Telescope and so on. So they're sort of astronomers, even though somebody else has built the telescopes and somebody else is probably processing the data. And then, of course, you get the theoretical astronomers who you know, the skeletons in the cupboard, maybe. So the sky has belonged to all humans since we first walked on the Earth. And many of the indigenous people still have a deep cultural tie to the sky. It still means those same mythical things. The Polynesian tribes, for example, in the Pacific, navigated by the stars, and it forms a deep part of their culture. It's not there for others to tamper with willy-nilly. So modern astronomers' access to a dark and quiet sky is under threat. So, talking first about terrestrial radio telescopes, the unit that astronomers use is the Jansky, which is a very, very small unit of energy. 10 to the minus 26 watts per square meter per hertz. So that's effectively saying you've got something up there shining radio waves down at the ground. It's how much energy, one Jansky is 10 to the minus 26 watts in a square meter for every 1 hertz of your radio receiver bandwidth. So what does that mean in practice? So, oh yes, and astronomers do often use millijanskys, as if the Jansky wasn't small enough. So 1 Jansky is the energy that you would receive on Earth from a mobile phone transmitting from Uranus. So the Jansky is an incredibly small amount of energy. In fact, if you do the calculation, it's slightly beyond Uranus. Right down to at the bottom, the same telephone transmitting from the lunar surface, 100 million Janskys, significantly more powerful. You've got Cassiopeia A, the supernova remnant there on the right, and that 2,720, and that's often used as a standard calibration for the energy coming off and being received by a receiver, even though in fact it is varying, because it does slightly irregularly, but it does decrease on average by 0.7% per annum in its energy, presumably as the remnant cools down. So the main problems are caused by, as I said earlier, mobile phones, TV, radio, computers, cars with a noisy ignition, aircraft going over, and so on. Okay, so the first satellite launched was Sputnik back in 1957. And since then, there have been nearly 26,000 satellites launched and about 15,000 satellites still active in orbit as of about 3 weeks ago. So that's satellites launched. Some of those may still be up there, but they've died. Some of them may have re-entered. Some of them may have been put into a graveyard orbit, deliberately out of the way. But 15,000 nearly still active. The early communication satellites were monsters compared to the ones we use now. Typically very large, 6 to 8 tons, and placed in geostationary orbits, 35,786 kilometers, give or take an inch or two, above the equator. Geostationary is when they're above the equator. Geosynchronous means they may be inclined. Each satellite there can see up to 42% of the Earth's surface. From that altitude, from that far out, you can see 42% of the Earth's surface. If you have 3 satellites spaced out around that equatorial orbit, that should be enough in principle to be able to cover the entire Earth, apart from a little disk at the top and bottom at the poles. And you'd have about a 40-degree overlap at the edges of each satellite's field of view. Problem is that the satellites out there have a long latency. The time taken to send a signal up and then come back is there about a quarter of a second, which doesn't matter if you're streaming a film on Netflix and it's coming via satellite. It doesn't matter if it's all a fraction of a second later than it left the satellite, because it's just pipelining, it's coming through continuously. Where it would matter is if you're doing, for example, constant negotiation, where you're doing business communications or something like that, where you've got to make bids and listen to results coming in. If you've got a quarter-second delay between things, that could cost you millions. So it's not good for that. And you needed to have sensitive receivers and powerful transmitters because of the distance. Big satellites, large solar panels to be able to power those transmitters. And they were expensive. They were the kind of things that very big companies or countries could afford to launch, not small companies. But satellites became smaller. The electronics became cheaper and smaller and required less power, which means that you could use smaller solar panels. And the cost of launching a satellite came down. So now you have low-cost satellites launched into perhaps 340 to 1,200 kilometers altitude, officially low Earth orbits up to about 2,000 kilometers. But most so-called low Earth orbit satellites are up to about 1,200 and not much more. Problem is, with them being so much lower down, instead of seeing 42% of the Earth's surface, they can now only see about 2.5 to 8% of the Earth's surface, depending on how high up they are. So if you're going to get coverage, you need to have a lot more of them, which is why we now have megaconstellations with thousands, tens of thousands of satellites, simply because they are operating so much lower down. It does mean you have the advantage that because not only do they need less energy, but also because they're lower down, their transmitters don't need to be so powerful and their receivers don't need to be so sensitive. So you can make everything smaller. And the other advantage is that the round trip signal time is now less than 10 milliseconds. So this is the success that Elon Musk has had with his Starlink satellites. And you can see here, this configuration here is what's known as a Walker configuration, where effectively you have a series of orbital planes at a certain inclination. And you have several of them which are staggered, each one rotated relative to the other one. And you may have several satellites in each orbit and several in each of those planes. So that way, if you had, for example, 24 planes with 24 satellites, you'd have 576 satellites altogether. So this was the early version of the Starlink satellite. You can see here, you've got them stacked up inside the fairing in the nose cone. Here, when they're launched, they unfold and initially start out flat in a low orbit to be checked out to make sure everything works. If they don't work, if they're not responsive, then they will re-enter fairly quickly from that low altitude. And then you raise them to a higher altitude and they go into this configuration. The satellite body is down here and the solar panels here, obviously vertical, facing towards the sun. The underside, the nadir side of the satellite body, points down to the ground so that the receivers and so on, transmitters are underneath. Problem was that they turned out to be quite bright. The first thing they tried to do was to put a black proprietary matte black paint, Vanta black, onto the satellites to try and cut down the light reflected. Problem was it also caused the satellites to overheat. And if you raise the temperature of the satellite, then they wear out faster and their lifetime is shorter. So SpaceX tried it, but they weren't happy with the result, and it only produced about a 0.7 magnitude decrease in brightness. Next thing they tried was this down here with visors on the side. You can see the little flip down visors. This is the back of the solar panel here facing the sun, and these dark areas underneath here are the shadows of the visors cast on the underside of the body. And so the idea here again is you make the underside darker so that it's not as bright. This also works, but again, only about 0.7 of a magnitude, which is no great improvement. And SpaceX eventually decided that the visors interfered with the laser communications that they want to put into the satellites to enable the satellites to talk to each other using laser links. So they moved on to later versions. So we've got here version 1.5, version 2, and version 3. And version 3, I shall come back to more later on because it's the model for some of the early designs of orbiting data center. Now, again, when I gave this talk ages ago, SpaceX were threatening to launch 42,000 satellites into orbit, and we were all aghast, knowing that it was probably the thin end of the wedge and others would want to join in. So this slide is obsolete because, for start off, SpaceX aren't going to launch 42,000 of these anymore. And 42,000 satellites is the least of our worries. This is the latest table showing the number of satellites that are proposed for launch. And you can see some staggering numbers here. I mean, to begin with, over here, we've got 2 Chinese constellations, which are probably going to be communications networks, a bit like Starlink. 200,000 satellites nearly, which way eclipses the 42,000 that Starlink were talking about. The Chinese have been going crazy on the industrialization of making satellites. They've gone overboard with production lines churning out satellites at a great rate. The Chinese will have no problem putting that many satellites into orbit, and I think their plan is to get them into orbit so that they can outdo the dominance that Starlink would otherwise have. There is a political element to this, to gain a foothold in space, because that's a problem. Space is big, to quote The Hitchhiker's Guide to the Galaxy. Space is very big, but it's not an infinite resource, in the sense that you still have to manage where your satellites go to make sure they don't collide with each other. And if you can take up 200,000 satellites can take up a shell around the Earth, it's very difficult to work out where you're going to put any others. Musk has already started doing that with Starlink, and the Chinese will presumably try and beat into the game on that. And then you've got down here, this one probably is a non-starter. This was eSpace, registered with Rwanda. I'm not sure that Rwanda are a great spacefaring nation. They haven't withdrawn it, but they also haven't said that they won't be launching that many, so they may not get launched. You've got OneWeb down here, the UK constellation. Out of the 31 constellations here, 11 of them are Chinese, so they easily rank alongside the US. We've got here a French constellation, 116,000, but this one here, ODC means orbiting data center. This is the one that SpaceX announced fairly recently, of putting nearly 1 million satellites into orbit. And when someone like Musk says he's going to do it, you have to sit up and listen. Although, again, it may well be that what he's done is put a filing into the FCC, the Federal Communication Commission in America, put the filing in to say we want to do this, but they may not actually use all of the slots available to them. StarCloud is another company, and I'll talk more about both of those later. And Sunrise is another data center company. So you can see that down here, this is a total of just over 1.8 million satellites. Probably not all of them will get launched, but it does rather put 42,000 into the shade. It's a bigger problem than maybe we ever anticipated it would be. And I would guess that probably many of these will be launched within the next 10 to 15 years. And the data centers maybe will start to be launched within the next 5 years. Not that many, but the number will grow. Now, I was concerned about where the hotspots, if you like, in the sky would be. So I worked on a web app to try and calculate what the density in the sky would be. Uses a very simple model where if you have the Earth, I can draw a circle, not too bad, and you've got the equator, and you've got an orbit that's inclined. Actually, let's not do that one. You've got an orbit that's inclined like that. So you've got a certain latitude here above the equator. So if this is the inclination of the orbit, the tilt to the equator, then this latitude here will be I degrees north, because if you tilt it up, it'll pass over the equivalent inclination at the top. So my analysis on this application, which I will show you in a minute, is that down here, the rate at which the satellites pass through a range of latitudes, infinitesimally small latitudes, if you like, is quite high, because here the inclination is the same as the orbit. Up here, however, if you take the same range of latitudes, the time it spends there is much longer, because the orbit is flattening out before the satellite starts to come down again. So if you do the calculus on this, literally do use calculus to do it, then you can work out what the density of satellites is over a particular area for a given constellation. And if you add up all the constellations, you know how many satellites there are over a particular latitude range. The next step is to say, Joe Soap is over here looking in a certain direction, and what will he see of that density in the sky? Especially given that he may see that density obliquely, which means it will look denser than it actually is, because it's foreshortened. So that's what this does. If I can now switch it back to the app. So F11. Switch to sky stats.
You stop sharing here, you share there.
Okay.
If you go out full screen here, it'll be effortless.
Yeah.
Go to the gas meeting here.
I'll go back to the gas meeting, share it there. Okay.
So stop sharing here. Yeah, that one.
That one. Okay. Share, and then back to that.
And you can do F11.
F11. Hide that. Close that.
Yeah, I think you can click on that. Doesn't go away. There we go.
Okay, right. So what this application shows here is down the left-hand side a list of constellations that we know about at the moment. And it's got the sky. The circle represents the sky. There's a scale along the side where the color represents the satellite density, number of satellites per square degree. And on the right-hand side, you've got the observer's latitude. So if we take, for example, just the Starlink satellites here, then we have the observer here at, say, 51 degrees north. Let's make it a little bit more obvious. So you can see here that this shows where the hotspots in the sky are. This is not necessarily where you will see satellites. It's where they are. They may be in the Earth's shadow. But to do a full analysis, I would have to put in the time and the date as well as the latitude to work out where the shadows are. I haven't got that far yet. As you hover over this, you can see, for example, I've got an alt-az grid you can put on, 15 degrees in elevation and azimuth. So over here, for example, we've got 0.0023 satellites per square degree, which doesn't seem like a great deal, but that's what, about if you took 400 snapshots of the sky at that point, one of them would have a satellite in, if they were the only two constellations up there. There are more down here near the southern horizon. I did cheat slightly because if you're in the southern hemisphere, you get exactly the same pattern, but the other way up. So all I did here was for southern latitudes, I just flipped the labels over without redrawing the screen. It was the easiest solution. If we go and look, for example, at this SpaceX one here, this is now well and truly saturated the scale range that I'm talking about here. And you can see, let's go to a different latitude, you can see more easily. You can see here that we've got rather more. This has got 2.4 satellites per square degree. So if you took a snapshot there, the chances are that every snapshot you take would have 2.5 satellites there in that picture. So just that, adding that one orbiting data center constellation adds an incredibly large number of satellites to the sky. And even here at higher altitudes, you've still got sort of 3 or 4 snapshots to get a satellite. If you add in star cloud as well, and maybe add in these 2 Chinese ones, very quickly you're seeing that the numbers are getting quite big, and certainly down here nearer the horizons, 30 satellites per square degree. And I've calculated this manually using spreadsheets, and it works. And I've calculated this is all written in TypeScript, and uses pixie.js as the graphics package, and it uses WebGPU to do the rapid calculations. So you can see here down there, the last one I did was 895 million calculations in 0.28 of a second. So that's pretty fast with a GPU. If you do this on a computer without a GPU, it takes a few minutes. So it makes a big difference to use a compatible graphics card. It still works though, just slower. If I turn all of the satellites on, all the constellations, here you can see that there really are a lot of satellites here, and down at sort of 30 degrees altitude, you're still here you're talking about 3 satellites. Here you're talking about 3 satellites. Over here, you're talking about 7 or 8 satellites. So if all of these are launched, astronomy, as far as I can tell, this is an existential threat to ground-based astronomy. So write to your MP, not that it'll do any good, write to Donald Trump, which will probably have even less effect. But this helps you visualize where the density of satellites in the sky will be. Okay. F11, I'll close that tab down. And I need to stop sharing. And do I need to share the...
No, you have to share on the other. I go to your laptop.
On the other laptop, okay.
Go to the laptop, yeah.
It's, I think. Okay, right. Okay, so these numbers really are just numbers, but when you see them visually displayed like that, you get a real impression of how much the night sky is going to be affected if they're all launched. So, I recommend this other one, satellite map.space, by the way. It's very good. It also has a section, satellite map.space. There's a section where you can look at close approaches of one satellite to another, and some of them are surprisingly close. So I want to move on to the visibility of satellites, not just whether they're there or not, but how visible they are. And we've got here on the top diagram, we've got a diagram which is to scale, apart from the oversized observatory. A horizon line, satellites orbiting at 1,000 kilometers altitude, and the sun is 15 degrees below the horizon. So anything above that purple line is going to be illuminated by the sun, and anything which is below the purple line on the left-hand side here is going to be in shadow, in the Earth's shadow. So all of the satellites from here round to the horizon will be visible. And in particular, the satellites which are here in the glinting satellites area, their underside of those satellites is going to be roughly parallel to the beam of light. So you're going to get glinting reflections off the underside of those satellites. And the reason I've chosen 30 degrees above the horizon is because that's probably where you do most of your observing, is above 30 degrees elevation above the horizon. And certainly for professional astronomers, they don't do it too far down, close to the horizon. When the sun goes further down, 30 degrees below the horizon, you can see that now there is a part of your viewing area where the satellites are now in the shadow. So that's why you see satellites going across the sky, possibly blinking as they tumble, but at some point they wink out, and they do that because they disappeared into the Earth's shadow. So the relevance of all that is, again, some of you may have seen this. This is an impression of where you have the tropics of Cancer and Capricorn. I think I've got this the right way around. And this shows you the North Pole here at the same angle as your latitude above the horizon. This is the point where the sun is summer midnight, and down here the sun winter midnight. So there's quite a range here between 15.1 degrees below the horizon to 61.9 degrees below the horizon, and it does depend on what latitude you're at. This was done in PowerPoint. I'm going to have to convert it to LibreOffice, and I'm rather dreading that. So it depends on the season, and it depends on how far after sunset as to how far the sun is below the horizon. So here we've got the satellites being illuminated at 4 different orbital heights, 290 kilometers and up to 1100 roughly kilometers. And this is the angle of the sun below the horizon. So you can see that even in the middle of summer at these latitudes, where the sun only goes down to about this point, 15 degrees below the horizon, most of these satellites here are still visible, still illuminated. In the wintertime, we're off the left-hand end of the scale here, the sun is 61 degrees below the horizon, which means that just about all satellites at those altitudes will be in the Earth's shadow. So there's a big difference between how many satellites you'll see in the summer compared to how many you will see in the winter. Doesn't mean they're not there. For radio astronomers, clearly a problem. So the biggest impact will be on the wide field camera telescopes. So the Vera Rubin telescope is a prime example of this, with a 3.5 degree wide field of view and an incredibly sensitive CCD camera. This will survey the entire sky every few days down to 24th to 27th magnitude. depending on the filters they're using. Incredible amount of data coming back. Problem is that when you get a satellite streak go through that field of view, the CCD sensors can be saturated. So you can have, say, a gas cloud, which will form an image on the CCD, but it doesn't saturate it. If there is a star behind the cloud, it might shine through the cloud, not a problem. But if you have something like a satellite come through the image and it's so bright that it literally fills the CCD cells with energy so that they look white, then you have no way of knowing what was underneath that streak. It's a bit like having an electric meter and you put it onto a 12-volt battery when you've got the meter set to 3 volts. The needle will go clunk and wrap itself around the one end of the scale. You don't know what the voltage is because it is the voltage is so high compared to what you've set it to. So in the same way, you're going to lose the details underneath the streak. Plus, CCD sensors have this problem that they will produce artifacts. If you saturate, some of the energy overflows into a neighboring circuitry. And so these parallel streaks here are effectively echoes caused by the saturation of the principal streak. So it's not just the one streak you need to worry about, it's the echoes as well that could be too bright. And then there's another problem, which is that Vera Rubin will take a picture and then a few seconds later it will take another picture of the same part of the sky. It's difficult to completely clear down the CCD sensor between one shot and the next when you get saturation like this. So you may even get a ghost of the previous picture still there in the sensor. It's a big problem for the Vera Rubin telescope. And obviously, the more satellites you have, the more of a problem it's going to be. Now, the IAU, if I can remember it, the IAU Center for the Protection of the Clear and Dark Skies, that's not all of it, something like that. I should know because I'm a member of the IAU CPS panel that works on this. They've called for a maximum brightness for satellites of 7th magnitude at all times. So that's below naked eye level. So your indigenous tribes and your casual stargazers should not be able to see the satellites going over. It doesn't make it much easier for the astronomers, because for astronomers, 7th magnitude is still very bright if you're using a telescope or binoculars. There are techniques being developed. The SatHub group of the IAU CPS division, they are developing software that will attempt to retrieve the data behind the streak. They obviously can't do that if the streak is saturated, but they might be able to do it if it's not a saturated image, not a saturated streak. It's called mask remove or something. I can't remember the name of the software, but they've been actively working on that. They also have to deal with curved trails. They've also got to deal with trails where the satellite's tumbling, so it's a dotted line. It's not a straightforward saying, oh, there's a line there, we'll work it out. You've actually got to work out what's happening to the trail across the image. And they're using artificial intelligence as well to train the algorithm to do it. And it's a problem for spectroscopy, because if you don't actually look through your telescope or take a picture of the sky, you're doing a spectroscopic analysis of a particular star or something. If a satellite goes through your image, you don't know it's done it, but it will pollute the spectrum, because it'll pollute the spectrum with sunlight. So this is for radio astronomy here. Now we've got, this is part of the radio spectrum allocated to different things like emergency services and the military and so on. But there are parts that are reserved for astronomy. And these here, this is the link here for communication from the ground up to a Starlink satellite, and the blue ones are for Starlink satellites to communicate back down again. And they've been carefully positioned so that they are in between the reserved areas for radio astronomy. Big problem is that galaxies often have a redshift. That means that, for the new people, if a galaxy is receding away from us, the color of its light is shifted slightly towards the red end of the spectrum, which means that Again, if it's a radio signal, it'll be shifted down to a lower wavelength end of the spectrum, which means that galaxies don't actually stay, or what you receive doesn't stay within those reserved bands. So it's all well and good saying we've reserved it for radio astronomy, but it's not that straightforward. You also have the problem that a lot of these satellites, they emit radiation, like electromagnetic radiation, just because the noise of the circuitry working. The electrons racing around the wires can give off a signal. Unintended electromagnetic radiation, UEMR. And it was suspected, it's been suspected for a while, but fairly, well, recently, I was going to say recently, perhaps 6 to 9 months ago, the LOFAR telescope in the Netherlands detected clear signal as the satellite went through the field of view. They got a signal from the satellite, even though it wasn't actually broadcasting an intended signal. It was just literally picking up the signal from the electronics on board the spacecraft. So you've got UEMR even without the broadcasts. And of course, radio interference doesn't depend on whether the satellite's illuminated by the sun or not. For optical astronomers, the satellite's gone into the shadow. The worst problem you might have is an occultation where it passes in front of a star, it blinks out for a fraction of a second. But for radio astronomers, even in daytime doing observations, they will have the interference from these satellites. So what about satellites orbiting observatories? So things like the Hubble Space Telescope. This is just a quick schematic here, down here, where we've got the Earth, and this is curvature, and these are the altitudes of the typical altitudes for the Starlink satellites. So the curvature is about right. So you get a sense of the scale of how far the satellites are above the curve of the Earth's surface. This little green box here is expanded up here. So these are the satellite, the Starlink orbits, and the dotted black line is a typical range of altitudes for the Hubble Space Telescope. So obviously you've got to make sure you don't collide with the Hubble Space Telescope. That wouldn't make you very popular. But if your Hubble Space Telescope is looking straight out, then you're looking up through a relatively thin sandwich of, or thin set of shells of satellite orbits. And so the density of satellites above you is relatively well spread out. However, if you're looking down, say 10 or 20 degrees to the orbit, to the tangent of the orbit, then you're going to be looking through a lot of satellites as you look out. It's just the same problem you have with the atmosphere. You look up, the sky's dark blue, and you look that way, and it's almost white because you're looking through a much thicker layer of atmosphere going that way. Well, in the same way, the satellites cause more interference when you're looking lower down. So that's a big problem. They already estimate that the Hubble Space Telescope is losing about 2.7% of its images. This figure is perhaps even a little bit out of date. This was 2023. And of course, if they do launch as many satellites as I showed in my earlier table, then the Hubble Space Telescope is probably not going to do very well either. Added to this problem, if you see a satellite from the ground, you've got software that can remove the streak. For the Hubble Space Telescope, the satellites are actually out of focus. So it's not a clear streak to remove, but a ghostly smear that you need to try and remove. So you've got a different problem to remove it. And there are other telescopes, including one here on the Chinese space station, that will similarly be affected. So orbiting observatories are not immune to this either. So now we've got satellites that will cause problems, types of satellites will cause problems. A year or two ago, there was a Russian company called Avant Space who said, we'd like to put adverts into the sky. So you can see here, there's a picture of Piccadilly Circus with the Rolls-Royce logo made up from satellites up in the sky. And the idea is that you'd have the satellites up there in orbit and they would literally fly over and Rolls-Royce would pay money to Avant Space to do the advertising. Avant Space say, and then we can reconfigure the logo and it could be different for somebody else. Maybe they even talked about putting QR codes up there. So you point your camera, your mobile phone at the sky, and it'll take you to a web link, something like that, which sounds interesting, if slightly horrendous in theory. This is the idea, is that you would have this arrangement of satellites beaming a picture down to the ground. Now, this must have been done by the marketing department rather than a scientist. Because if you are Joe Soap standing here in the middle of the omega signal, what can you see? Nothing. Because the spots of light that your eyes are meant to see are all falling on the ground around you in the omega shape. Unless you're standing in one of those little spots of light, you won't see anything. And to see an omega shape in the sky, all of those spots of light have actually got to be converged to one spot, so that standing there, you see all of the spots and all of the satellites. That doesn't work. It's, as I say, it's the marketing people. So this was the idea of what you see, and I actually looked at this and I did some measurements, and I've written a briefing paper to say why I don't think this will work. And I said to Richard, I've got a briefing paper for this and 2 others, and I'll make those available for you to read. That gives a bit more detail as to why I don't think this will work. They actually have other logos, and this is, I've got too much time, haven't I? I actually counted the dots in each of the logos to work out what they've got. So that omega there is 20 dots, but they had a rather ambitious Huawei one at 78 dots. So they've got to have those satellites up there flying in close formation, but more than that, they've also got to be in the same plane, the same altitude, because if you're standing here and the satellites rise over there, you're going to see the logo foreshortened, look right up there, and then foreshortened again over there. But if any of those satellites is too far out or too far in, then it will not only orbit faster or slower, all the way around, slower or faster, but also it will very quickly get out of position. And as you look over to the side, it will look out of position because it's too far out, too far in. So you've got to get your positioning very, very accurately. So let's suppose here this is the Earth, and you've got these satellites flying on slightly inclined orbits with satellites on each one. What do you do when you get to the crunch point here where all the orbits cross each other? You've got them all in the same plane, all at the same altitude, and they're all going to come crunch together. So you've got to do something very quickly to make sure you spread them out. So technically, you've got a problem there. I also made the comment here that the ion thrusters they were talking about aren't big enough to move the satellites in a timely fashion to reorganize from one configuration to another, and also probably not powerful enough to avoid collision. I also made the company here that the company is Russian, so of course it's currently sanctioned, and they can find it difficult to find the necessary components, given that Russia is on a war footing, and they've sent a lot of their young men to the battlefield, so there aren't the young men there to actually build the satellites. And given that they are a Russian company, they're going to find it very difficult to find people who will buy their advertising space, especially Western companies. And if you remember back to that list of logos, most of them were Western companies. So I can't see anybody like Omega wanting to buy advertising space from the Russians for a while. And there are alternatives, because you have drones. And we've seen drones become very effective. You can have colored drones. You could put them below the cloud layer. I mean, you could imagine paying for your expensive satellite logo only to find that it's clouded out. It's a problem astronomers are all too familiar with. And this is an example of an animated drone display of a dragon. And wouldn't you really rather have that than something up in space? It's 3D, it's color, it's animated. If any, it's a bit jerky. I think it's not supposed to be jerky. I think it's because of the way we're doing this. But if any of the satellites fail, then you can fairly easily replace it, where it's difficult to do when one of the satellites up in orbit has failed. So I think drones are going to be the way that this kind of thing will go, rather than in space. And then the other problem is that if the public don't like seeing adverts in the sky, you know, they get them on TV with frightening regularity, and they get them in their magazines, and they get them on billboard. They may not want to see them in the sky. So it may be that companies will say, well, I'm not going to advertise my my product either via drones or in space, because the public will hate me for it and not buy my product. So that's always a possibility as well. So the next thing is a company called Reflect Orbital. They want to put mirrors into space. They want to sell sunlight as a service. So the idea is that you've got solar panels on the ground, and along comes sunset. And so you've got satellites up there orbiting in a sun-synchronous orbit over the terminator, so that they're permanently illuminated by the sun. But the mirrors are tilted so that they reflect light down to the ground. And the idea is that you can illuminate those solar panels and generate energy for a little bit longer. It turns out to be a very small amount of energy from any one satellite. And so the problem is that, yeah, one 18 by 18 meter mirror would generate about 22 milliwatts per square meter. And the sun is about 1,360, I think, watts per square meter. So it's orders of magnitude smaller. You would need a lot of mirrors. So Reflect Orbital said, fine, we'll launch 50,000 of them. They are putting up they want to put up a satellite called Earendel-1 as a proof of concept. And they want to do that sometime this year to find out how much energy actually comes down to the ground. Of course, it's going to come down through the atmosphere, so the beam of light is going to be scattered. And there's no guarantee that that mirror is going to stay perfectly flat. The frame it's on, it's a mylar film stretched over a frame. That frame is going to distort because of temperature variation. So that's going to cause scattering. You're going to get micrometeoroid impacts. It's going to be in a low Earth orbit at a point where atomic oxygen will eventually cause weathering of the surface and make the mirrors scatter as well. So I don't think it's going to work. And I think, realistically, I think that the prototype will be very disappointing, and that the millions of dollars that have been given to them to prototype this will, the investment, I think, will probably dry up. So I actually said this in my briefing document. I said, I think it's interesting, technically maybe doable, but I don't think it's going to be viable for solar panels and giving you extra energy. The other thought that they had was that you might have a big event and you may want to have extra light to illuminate your event. So they would, so you have a big rock concert or something like that, and they will illuminate it for you for a cost. I don't think that will work. So the other one is power generation, where you could have large solar panel arrays up in space, gathering sunlight, converting it into microwaves, and beaming it down to the Earth's surface. Oh, God, I'm running out of time. So again, that may well be a starter, that may work, but it's going to require a lot of satellites, and you've got to start considering what happens with microwaves being beamed down to the surface. Your satellites have obviously got to be able to turn off the beam if the satellite moves slightly. And also you've got to think about aircraft flying through the beam. How would they be affected? The theory is that it's too low. It's about a quarter of solar energy, the amount of energy involved. So probably not a problem. I know that the European Space Agency have been looking at this. So the next one is data centers. And this is going to be, I think, the big one, and this is going to be the one that will be a big problem for astronomy. We've got a very rapid growth in AI. That application that I showed you, most of it I wrote myself. I got Claude AI to help me a little bit with the GPU side of it. So I've used AI already in some of what I showed you tonight. I used AI for those cartoons earlier on. AI is going to grow a lot, for better or for worse, whatever the arguments. But AI does consume a lot of energy, and it requires a lot of cooling. At the moment, most of the AI centers cover large areas of ground out in the middle of an Arizona desert or something like that. solar panels providing the energy and water providing the cooling. That's fine. The water isn't actually used. It's recycled and goes through cooling towers and so on and so on, so it's not actually consumed. This table on the side here shows the largest data centers in the world. And you can see that some of these will consume huge amounts of power. I mean, the one here in Norway, up to 1,000 megawatts of power, so up to 1 gigawatt of power, which is a lot of energy. But of course, Norway are lucky. They've got a lot of hydroelectric power, so it isn't so much a problem for them. Added to which cooling works very well in Norway because it's a lot cooler there. So we're going to see a lot more of these data centers being developed on the ground. But you've got people, especially those who've got satellite businesses, who are saying, well, why don't we put these data centers into orbit? Because we've got lots of free sunshine up there. The problem you've got then is you've got to work out how to cool your satellites down. So this company, StarCloud, they started out launching their first satellite November last year. And within a short space of time, within a month or so, they got it running an AI model called NanoGPT on the single card, AI card that they launched on the satellite. So they've got proof of concept on a very small scale that they can make AI work in space. One of the problems is that radiation might occasionally cause bits to flip. And they're saying, well, if you've got an inferential model that's doing all sorts of woolly hand-waving arguments to come to a conclusion, it doesn't matter if the odd bit is out somewhere. It doesn't work so well if you want to do precise calculations where every bit is important. They plan to launch StarCloud 2 with a cluster of GPUs in 2027. And they will be in a sun-synchronous orbit in the same way as the reflect orbital mirrors are talking about. And they've filed for permission to launch 88,000 satellites as data centers. So their ambition over time is to go up to a 5 gigawatt data center. So this is the idea here. You've got a central spine onto which you attach these modules, and the spine is meant to be up there for quite some time, and the modules can be removed, re-enter, replaced with more modern equipment, so that you can grow or shrink it according to demand and so on. So they have a potentially workable solution, and they're going to take a few years to get up to it. They are talking about a 5 gigawatt system, and you're not misreading that. This will be a 16 square kilometer solar array. So that's 4 kilometers on a side. So you're going to have problems with occultation, and you're going to have problems presumably with glinting off the solar panels. And you've got all sorts of other things to consider, like drag, and they want to put the initial ones at a lower orbit and put this one at a higher orbit. They're hoping for a 15-year lifespan, but their CEO says, yeah, we may be a bit optimistic with that. The large solar panels would, let's say, glinting and occultation. The other problem is they need to cool these data centers down, and they're planning to use radiators. Great big black radiators, and they will use cooling fluid around the system to cool the components down, and they've got a radiator on the back. Now, StarCloud said that they were going to operate their radiators at 20 Celsius. And if you use Wien's law, which I put there, it's a very simple formula, 2,900 divided by the temperature in Kelvin gives you roughly the peak wavelength that's being emitted. So if you're 20 Celsius, 293 Kelvin, call it 290, that's 10 microns. So all of those radiators will be glowing at 10 microns. So now you infrared astronomers who are trying to observe things in the 10 micron band, which is a window in the Earth's atmosphere that lets 10 micron radiation through it, now have this huge array of 10 micron searchlights in the sky you have to contend with. You could use a higher temperature and use smaller radiators, but they'd be brighter. Or you could use a lower temperature so that you shift where the peak is, but they would have to be huge radiators, and they would be much bigger than the satellite. So sorry about the amount of writing on here. There's a lot to say, and my memory's fading, so they remind me what to tell you. Elon Musk has recently merged his XAI company with SpaceX, and he's entered a draft initial public offering, effectively floating it on the stock market. The estimate is that it will be a float of $1.75 trillion, which will be the biggest float ever onto the stock market in history. It may be coincidence, of course, that his plan to launch 1 million satellites as a money-making venture was timed very nicely to coincide with offering the company for public purchase. It may be that the 1 million will never happen. It's just a way of boosting of course I can't say this, but it may just be a way of boosting the sale price to say, look what we've got in the pipeline. So that, again, the satellites were placed in sun-synchronous orbit. You can see here the satellite on the side here that is the suggested version, is a slightly larger version of the V3, but it is huge. Those solar panels are 172 meters wide. That's an estimate based on 1 or 2 diagrams that they've given, and you're adding some of the numbers up sensibly. But that makes the satellite wider than the Starship V3 that he wants to build. One of the problems I can see with this, what happens if they want to rotate it? The strain on the joints and the framework trying to rotate 172 meters worth of solar panels is going to be immense. He plans to have these data centers communicating with each other by laser across multiple satellites. And the idea really is that if you're doing, for example, weather observations or astronomical observations, or you're analyzing images of something going on the ground, you want to process that data. And normally the way you do it is your satellite would beam all the data down to the ground, and you would have your data centers on the ground crunching through the numbers, working out your weather forecasts. So they're saying, well, what if you've got all of these in orbit? The satellites beam the data instead to one of these orbiting satellites. The numbers are all crunched in orbit, and all you get is the weather forecast. And much easier, much less data needing to be transmitted. So you do the work up there rather than down on the ground. But they will have the same problem as StarCloud in getting rid of the extra heat. This little appendage here on the side is the radiator panel that they're proposing for the SpaceX orbiting data center. So these are smaller satellites than StarCloud, but they're going to have more of them, and they're going to require more management, particularly in the traffic in orbit. And they're going to have to launch these and replace them when they fail, and replace them every 5 to 7 years when they start to wear out. And Trump has appointed Brendan Carr as the head of the FCC in America. He's absolutely a Trump acolyte, and he has said he wants to accelerate the licensing process for satellite launches, which means that he wants to do it more by rubber stamping than by going through the details of whether it's a good idea or not. And in particular, one of the things that we've been pressing for a long time is that satellite launches should be subject to the National Environmental Protection Act. In other words, you've got to work out what impact is that launch going to have on the environment. And Brendan Carr will almost certainly say, ignore all of that. Yeah, you can do it. So I think we'll find that Musk will get a rubber stamp yes, and Reflect Orbital will probably get a rubber stamp yes, and StarCloud, because they're American companies, and it's in the current US administration's interests to basically promote AI and to promote American business. So they don't care about the environment, quite clearly. Space date, how much time do you want me to carry on for?
Yeah, I think maybe you could, we've had about an hour or so.
I've got about another 7 slides if I go very quickly.
Okay, yeah, maybe.
So space debris is clearly a problem. This is an example of a solar panel with a micrometeoroid impact. And so solar panels will need to be replaced in time. And so there's going to be a big business going up servicing those data centers and their big solar panel arrays. No part of a satellite should explode. No battery, electronic, or gas components should explode. And this was an important factor. However, back in December last year, there was a Starlink satellite that suddenly fell apart. And there are several tens of pieces of debris that came off this satellite back then. And down here, they've said that they're working to make sure this doesn't happen again. But then in March this year, it happened again. So it's slightly worrying with the number that they want to launch, that compared to what they've got now to how many they want to have, that you could potentially have more problems with satellites just falling apart, creating more and more space debris. There are strict rules about how you deorbit the satellites. I won't go into this in great deal, but basically the aim seems to be to get rid of satellites, old satellites, by having them re-enter. They burn up in the atmosphere, which may seem fine, except that satellites are made of aluminium and rare earth metals that make up the electronics. And as they come down in the atmosphere, these will vaporize at about the same altitude as you see meteors vaporize. And so you're now leaving fine particulate matter of aluminium, and aluminium is reactive, so it'll react with the oxygen, form aluminium oxide, is like a fine soot, if you like, of aluminium oxide. But the rare earth metals will vaporize as metal particles in the atmosphere. Many of the rare earth metals are particularly catalytic in their action. And they're going to be deposited into the atmosphere up roughly where the meteors are. And those particles will slowly waft their way down over a period of perhaps 10 or 15 years to where the ozone layer is. And there seems to be some evidence that alumina will destroy the ozone layer, and helped by the catalytic effect of these rare earth metals in the satellites. So just as we're getting over CFCs and repairing the ozone layer, we may have another problem. And if we realize that this is happening, you've still got 10 or 15 years worth of backlog of stuff coming down to damage the atmosphere. So I'll skip over that. So down at the bottom here, if you had 500,000 satellites in orbit, that means deorbiting 6,000 to 8,300 per month. You've only got to look at how many there are and say it's a 5 to 7 year lifetime, and having to launch the same number to replace them. So you're also polluting the sky with the rocket exhausts as well. And also with those satellites going up, raising up to their final orbit and coming down to re-enter, they're not going to be oriented for optimizing their darkness, their dimness to astronomers. They're going to be optimized on the way down. They're going to be optimized flat on to increase the drag on them, put the solar panels flat on. They will slow down faster and fall in faster if you do that. And when you launch them, you want them parallel to the ground so that they have the least amount of atmospheric drag on them. So that isn't necessarily going to be best for astronomers. And you could have as many as 7,000 bright satellites in the sky around the globe, with re-entries coming in at 233 per day. That's roughly 1 every 10 minutes somewhere around the world. So this is just a graph showing the number of objects being launched. Skip over this. You also get some ionization effects when the rockets are launched. This is a Starlink rocket causing ionization, and it's the same red color that you get from Aurora, and it goes away. The chemistry resets itself when the sun comes up, but you don't know what permanent effects there might be. There has been some talk about using wooden satellites. This is a Japanese project, LignoSat, using a particular type of maple wood and using traditional Japanese jointing techniques with a metal frame around the outside. And the idea is that wood will burn up much more effectively than the aluminium frames. The first one they launched failed very quickly, but they suspect that's not the wood's fault. And they're planning to launch another one, LignoSat-2, later on this year. Not quite sure where that's come from. Okay, so this shows you the jointing. Okay, and then possibly they can use wood for other things like lunar shelters. And then the part here saying we live in troubled times. We live in a time when satellites are being used for doing observation of what's going on the ground, looking at conflicts, reporting back to America or to Israel or to Russia or China. And we have all sorts of other problems, particularly with the tangerine tyrant we have over in America. And I also like Mango Mussolini as the other one. Science, astronomy as a science requires you to travel around to different observatories. It requires going to conferences and collaboration. And it's becoming very difficult to do that. In America in particular, there have already been people quite innocently going over there to attend a conference and being refused entry to a perfectly normal conference because for some reason the guards there didn't like the look of you, didn't like something you'd got on your mobile phone. They want to check your phones and your laptops and all those sorts of things now. We're having problems also because with COVID, recovering from COVID, still recovering, well, perhaps not really recovering from Brexit in this country. And we've got people whose attention is diverted elsewhere. We've got to increase our spending on defense in Europe because of the threat from Russia. And of course, that's money that could be spent on the sciences, but won't be. So we're already seeing some cuts, both in America and here. Some of the cuts in America are political. For example, NOAA, which basically researches the atmosphere, is one of the organizations that the Trump administration is trying to close down because for some reason they don't want the impact on the atmosphere to be recognized. So there's a screaming conflict of interests there. In this country, they've already been advised, departments have already been advised that astronomy, particle, nuclear physics cut by roughly 30% and some projects by as much as 60%. Those are huge. They're the biggest cuts we've had in this country ever. That's what those stickers were that I passed around. And we've got some tensions in the use of Starlink in Ukraine, with the Ukrainians using Starlink, with the Russians trying to use it and now being denied the use of it. And I could see other tensions arising from the use of satellites. And you may even find, particularly with an administration like the current one, you may say, oh, we don't like those people, we don't like what they're doing. SpaceX, you've got to turn Starlink off over that country. This is a digital sanction, effectively, that the Americans could apply to a country that they don't approve of. Well, do we really want that? And it's no wonder that several European countries are now trying to distance themselves from US technology. So France, for example, is going to stop using Microsoft products. Germany is going the same way. In government, that is. So we have grown up in an age where we've seen space as something wonderful and something to benefit us all, something to aspire to, but it's being abused by the likes of Elon Musk and the current American administration. You could have a situation where you will have, for example, the Russians decide to take down the satellites and increase the amount of debris, increase the amount of scattering in the atmosphere. So space is now being considered a theatre of war. Last slide. So this is what I covered. And we're having the rights to our clear and dark sky being deprived of, so children will not see what we have enjoyed. Thank you.
Thank you. Thank you, Paul. That was a really interesting and lot to think about after that talk, I would say. So I know we've gone on a bit, but we should have some questions. So does anybody have any questions?
Yeah, thanks. That was very illuminating. That's too bad a pun. On the very large solar panels, does that cause a problem with thrust on the satellites that they have to manage?
Yes, and they're talking about having to counteract light pressure. That's what you're thinking about, is it light pressure? And certainly Reflect Orbital are talking about actually using the light pressure to help steer the satellites. I have to say again, I don't think it's very practical using light to orient your mirrors, but that's what they've said. So yes, it's certainly an issue, especially with things that size. A 16 square kilometers solar panel array is bound to have light pressure on it. Significant light pressure, that is.
Anybody else? Okay. Run around here. Try and ask it that way. Yeah. I've got to anyway.
Who said that?
So you've been talking about satellites going up and the space junk, but there's also technologies to try and remove some of that. Is there not? And how effective are those at the moment?
I think those technologies are still being developed. Problem is they can only usually deal with one satellite at a time. Maybe they could do a few, maybe a couple in a day. But at the rate that they're talking about launching them, I think they're going to swamp any efforts to actually remove dead ones from orbit. So it may be a hope. I think one of the other hopes maybe is to increase the fuel capacity on the satellites so that they don't fail because they've run out of fuel. And one of the other issues, of course, is that the risk of collision goes up roughly as the square of the number of satellites. If you have 10 times as many satellites, you've got 100 times the risk of collisions if they're in a similar space. So, I mean, one solution is just don't launch as many. You've got to have traffic management to work out, make sure they don't collide with each other. But all of that maneuvering to avoid collisions will use up the fuel faster. So there may come a point where you've got that many satellites up there burning through their fuel so quickly that you've counteracted the effect of putting the extra fuel on them. So there may come a limit there. One of the other limits that I've considered is the one of insurance. Insurance companies need to insure against these satellites coming down and injuring somebody or colliding with another satellite. The Outer Space Act says that whichever country launches a satellite is responsible for it. If it collides with somebody else's satellite, then that country should pay compensation. So that may be an insurance issue as they get to be more and more and more of them. Doesn't worry Elon Musk because he doesn't insure his satellites. Maybe third party, fire and theft. But I think that may also be one of the other factors is insurance. Tony?
I was looking forward to you to your talk and to your coming. Now I'm just depressed. Is there any good news?
Give me a couple of days to think. At the moment, no, I don't think so. My only hope is, for more than just astronomy's reason, my only hope is that the midterms make Trump into a lame duck president and the Democrats can start to seize control back and sanity will eventually resume. And the environment will become important. And at the same time as the environment is starting to be considered, they will start to put more regulations in place. Maybe an international body that regulates what is launched and which orbits they go into and how many are launched and things like that. There needs to be more done. There are a lot of people working on the regulatory side of it.
Okay, thank you. I think we'll leave it there. So thank you very much.
Can I put... If you go to the FAS YouTube channel, there was a 2-day webinar, so that there are two, I think they're 5.5-hour videos given by experts about what I've just talked about. Obviously, it's a couple of years out of date by now, but all of the principles apply, and there are some very good people on there. You watched them, didn't you?
I watched it live, so
yes.
Yeah, it is really good. Okay, so maybe we come back at 10 past, and then we've got tea and coffee outside if people haven't seen it before, and we'll come back and Glenn's going to give us a fantastic demonstration of this sea star. We're going to do